Yes, homework is graded on correctness with some leniency in terms of, the steps. So, for example, on the one where you have to calculate the change in Earth's temperature, if the albedo changed, if you incorrectly calculate the albedo change, we won't penalize you for calculating an incorrect temperature as long as your math is correct. You do not need to submit the Excel spreadsheet as long as you make sure that you've copied everything that I've asked for into the document, right? So here where I ask you on part 2 in particular to make sure you've pasted your graphs. Obviously, if you don't have them in the document, then we won't be able to grade you on that. Because we're not going to really go through all of your workbooks, your Excel worksheets, to see all of the calculations per se. No, so you don't need to submit those. Just this worksheet, this Word document. Okay. Pages will be difficult. I'd prefer if you submit it as either a Word document or PDF, because if I don't have pages, which I don't, then we won't be able to open it. So if you can save your pages as a PDF, PDF is pretty universal. That would be great. Yes, the lowest quiz score is dropped. And there might have been some questions about the quiz. I'm waiting until probably, unfortunately, next week because there's always a few people that join the class late. And so I'm just giving them an opportunity to take that quiz. And so I will go over some of that information once everybody has had the same time to finish the quiz. Yep. All right. Any other comments, questions about the homework, anything? I'm still happy to answer questions, through email, through Discord. I'll just mention, I posted in Discord this morning that one, we are maybe on different time zones, so that can be problematic in terms of me responding. But two, I have a 14-month-old son. And so I'm going to bed at like 10 p.m. my time, usually earlier, and I'm waking up quite early. So I just cannot be on my phone, after a certain time. So if I'm not responding to you, this is a lesson in trying to get things done a little earlier. I had a few of you messaging me this weekend, which is great. I, have a bit more freedom and flexibility on the weekends to respond. But if you're starting your assignments right at the due date, I can't really provide much feedback or much help. So just try to get started a little sooner. When you run into questions, then you can ask for help. All right. So if you do have any questions about homework 1, just send me an email, Discord, before like 7 p.m. and you'll probably get a response. Okay, so we will then move on. Okay, so today we're going to continue on talking about heat and moisture, the moisture in our atmosphere, right? You talked a little bit about how latent heat, that energy needed for evaporation and condensation, is quite a lot. And that's one way that our Earth system, our climate system, can move a lot of excess heat from the equator to the areas on the planet that don't get as much heat, say the polar regions. Okay, so we'll continue talking about some of that with relative humidity and moisture today. So for today's warm-up, I want us to look at this graph. This is from the Intergovernmental Panel on Climate Change, IPCC's Fifth Assessment Report. So the first thing I'd like you to do is to look up and define what is meant by radiative forcing. Okay, and the units here are watts per square meter or watts per meter squared. And then think about what this data is showing us. Okay, so I will give you about 3 minutes on this. You can start typing in your answers whenever you have them, and then we will discuss. I'm setting a timer right now. All right. So, yes, I'm reading through what you're all entering as best as I can. It's always fun. It moves through. But radiative forcing, as many of you looked up, is the change in our energy balance due to the addition or removal of different things in our climate system, right? So we talked about how much energy Earth is getting from the sun, and then, how much gets reflected. And we determined that after we account for the albedo, that 30% that gets reflected, we get about 340 watts per square meter of energy at the Earth's surface. Okay. And what we're doing, human activity is doing, is it's impacting some of our greenhouse gases, right? Carbon dioxide, methane, and those additions, those extra molecules of carbon dioxide and methane, have a warming impact, right? So we can see that carbon dioxide's warming impact is about 1.7 or so watts per square meter right now, or as of the publication of this assessment, which was actually a few years ago. And then we can see other activities like human activities such as changes in clouds due to aerosols. So we put more clouds into the atmosphere through things like jet exhaust, right? So those are called contrails. It's actually a really interesting phenomenon that some of our planes, our aviation, actually can help negate some of that climate impact from from carbon emissions. But then you also have carbon emissions from the jets and the aviation, so it's not exactly one-to-one, but you can see here that some of these clouds actually have a cooling effect, right? So if we take into account all of these positive warming radiative forcings and then the negative cooling forcings, we get a total forcing on our planet right now due to human activities. That's about 2.5 watts per meter squared, which means that for every square meter on Earth, human activities are adding an extra 2.5 or so watts per square meter, and that is increasing temperature. And these little bars on each of these lines, these are our uncertainty bars. Basically, how much error or how much do we not understand that relationship or that forcing? And what you can tell is that we know quite well that carbon dioxide levels are impacting our temperatures and our radiative forcing. The ones that are still more uncertain are our aerosols. Okay, so for example, black carbon from fires has a warming effect, but there's also a cooling effect from other aerosols. So they kind of, depending on where they are, can have both a positive and negative effect. So we don't have as much certainty on those, as well as changes in clouds, right? So I mentioned clouds can impact our albedo, but our uncertainty, that error bar, is quite large. And so when you add all those uncertainties, we get something at the bottom here but we can still see it's well above positive or zero, meaning we know that the changes in the warming side. Okay, so these are really important graphs. We will look at these, and these are ways that scientists can send information to policymakers to say, hey, if you wanted to do one thing to help with climate change, it would be something on these red bars, right? Something in the warming, impacting carbon dioxide, methane, and some of these halogenated gases, and we'll talk about those towards the end of the semester. Okay, so here's Earth's energy balance, as I mentioned, right? We talked about the incoming solar radiation, how much gets reflected, right? So this here, this is radiative forcing, how those gases and changes to our system are impacting how much energy gets trapped by the atmosphere in the Earth system. All right, so today we'll continue talking about our atmospheric circulation, and then we'll start talking about moisture and how we can get clouds and how that can impact our climate system. Okay, so remember on Thursday we talked about latent heat, and that is the energy that is required to change phase, right? So you can technically have both liquid and vapor at 100 degrees. The difference is whether or not you have that latent heat of vaporization, this long segment here of energy to go between liquid and vapor. Okay, so let's just recap. How much energy is needed to evaporate 1 gram of water? Well, it's 540 calories per gram. Okay, if we had more than 1 gram, we would multiply it by the number of grams. And how much energy is needed to freeze 1 gram of water? Okay, so that phase change from going from a liquid to a solid, we would need 80 calories. Now, the way our Earth system gets that energy is through the environment. Okay, so imagine I am just some air or some moisture kind of hanging out in the atmosphere. In order for me as that air, that moisture, to completely evaporate, I have to get that heat from the environment, right? So we talked about the difference between heat and temperature. Everything has heat, and the more molecules, the more heat you'll have. And so we can think of the fact that air, our atmosphere, has heat, and that heat can be used to evaporate and condense water. Okay, so what about our warm air? We talked about how air is heated differently at different places on our planet. What's going to happen with warm air? Is our warm air going to rise or sink? Okay, hot air, warm air, and also warmer, right? So it doesn't have to be hot. It just has to be warmer than the rest of the air near it, will rise. Okay, and this is the idea of hot air balloons, right? You heat the air inside the balloon, it is warmer than the environment around it, the air around it, and it will rise up. We also talked about Coriolis, this deflection of things that aren't connected to Earth's surface because the Earth is rotating beneath those things like our air. So the Coriolis force is going to deflect air in the northern hemisphere. Is it to the right of motion or to the left of motion? Okay, so in the northern hemisphere, objects, air, winds are deflected to the right. Okay. because of that Coriolis effect, and they'll be deflected to the left in the southern hemisphere because of the Coriolis effect. And this again is in the path of motion. So you have to sometimes, maybe turn your head a little bit to think about where the molecule or the wind is starting from and where it's going, and then it'll be deflected either left or right of that path. And then at the end of class, we talked about our 3-cell model, the way that we can think about our atmospheric circulation, both above us in the higher atmosphere and at the surface due to the unequal heating. So which of our 3 cells, the Hadley, the Ferrel, or the polar cell, is not thermally direct? All right. So, fun fact, Will Ferrell grew up in Irvine. He actually went to University High. Random fact I know. And the Ferrel cell is thermally indirect or not thermally direct. It is not actually driven by temperature differences. It's just there because the other 2 cells are being driven by temperature differences. Remember, at the equator, we have a lot of heating from the sun. And so our air at the Earth's surface at the equator wants to rise up. Okay, that warm air is going to rise up. It reaches the top of our atmosphere, that barrier, that boundary between the troposphere and the stratosphere. It can't continue on. And then it gets sent in both directions. The Coriolis effect and the fact that the air is no longer heated, it starts to sink because it's cold. Okay, that's our Hadley cell. And so that creates lower pressure along the equator because air is rising away from the equator. And when you take air away, you're moving mass away. That changes the pressure at the surface. And then around the 30 north and south, we create higher pressure at Earth's surface because we have air descending from higher up in the atmosphere. And all of that impacts our surface winds. Okay, so we talked about our 3-cell conceptual model. It explains the presence of that intertropical convergence zone, the fact that the surface easterly or trade winds are coming together at the equator, forcing air together and up to create clouds. And we'll talk about how we form clouds today. It also helped us explain where we have deserts on our planet and where we have rainforest. But what it's not able to explain is the circulation patterns that we see up in our upper atmosphere or upper troposphere. And it doesn't take into account the differences in land and ocean. Okay, it doesn't know anything about the fact that, our northern hemisphere has more land than our southern, and how that heating difference between water and land will impact smaller scale circulations. Okay, so again, here's our 3-cell conceptual model. And we call it the conceptual model because it's based on just a few concepts, right? That warm air rises, cool air sinks, and winds blow from high to low and are deflected by the Coriolis. And with those basic concepts, we actually are able to describe a lot of the circulation we can see on our planet, which is pretty cool. Okay, so understanding where we're going to have deserts, where we're going to have rainforests, why that is explained by this model. But as I mentioned, in reality, our land and sea are not evenly distributed on our planet. So the northern hemisphere, this is looking down at the North Pole on the left and looking down at the South Pole on the right. What you'll notice is that the northern hemisphere has a lot more land, and the southern hemisphere has a lot more ocean. And we know that those features, those surface types have different potentials to heat up and cool off. And so heating and cooling can impact winds, okay? And also topography, right? We, in our 3-cell model, didn't talk about the fact that, there are giant mountain ranges that will impact how air flows too. So when we look at our Earth in July, we will notice a few things. We get these what are called semi-permanent pressure cells in different parts of the world. So here, this is July. So if I'm looking in the northern hemisphere, say the Pacific Ocean, we get what's known as the Hawaiian High. And we also get the Bermuda Azores High in the Atlantic. And I'm focusing just now on the northern hemisphere because in July, that is northern hemispheric summer. And we know that land heats up faster than water. And so in summer, even in July, the oceans, in the summer season, the oceans are still cooler than the land, which creates a bit of higher atmospheric pressure over the oceans and lower pressure over land. And we actually see that over here, the Tibetan low, which is over land. Okay, so the land heats up a lot and creates a low pressure, right? Air rises at the surface, and then there's that loss of molecules or less molecules creating lower pressure. And so these are our semi-permanent pressure cells. These last for about a season rather than just a day, and they don't last all year. So they're not like the low pressure along the equator. These happen seasonally. Okay, you don't need to know all of these, but what you do need to know is why we get them. Okay, now if we switch to January, what we find is we get the Aleutian low off the coast of Alaska and Russia, where our ocean stays warmer in winter than the land. Okay, the land cools off much quicker, so we start to get more high pressure over land in that hemisphere, right? Again, we're just focusing on northern hemisphere here. And if we look over Siberia, big high pressure there because the land cools off a lot. And these lows and highs, again, we talked about how at our surface, air is blowing from high to low. And so these semi-permanent pressure cells are going to really impact our surface weather, what we see in terms of storm systems and whatnot. Okay, so the seasonal switching is really due to the change in temperature that each land and ocean experience. And they're not the same range because of that specific heat that we talked about on Thursday. Okay, so we switch between the high and low. And again, why is this? It's because of that change in temperature, or excuse me, yeah, change in temperature due to the surface. Okay. And so when we look, just a summary, the oceanic lows are the most intense during wintertime. Now, I'll tell you now, we're not going to talk too much about weather patterns in this class because this is about climate, but low pressure is where you get the weather makers, right? If you want a giant snowstorm to hit the Sierras and dump like feet of snow, you need low pressures, right? So we get low pressures over the ocean in winter. Now there's a lot of moisture over the ocean, which lends itself to helping produce these really powerful winter storms. Okay, and again, these are caused by the specific heat capacity of water versus land. Okay, so our three-cell model again describes our surface winds very well, but does not describe our upper atmospheric winds, what's actually going on above our head. Okay, well up above our head where our airplanes are flying. So if we look at this cool website, I want us to look right now. We're looking at Southern Hemisphere. The colors here, let's see if I can get my key up. The colors here tell you wind speed. Okay, so these pink colors are like 300 or 250 kilometers per hour, which is quite quick, moving quite fast. And you'll notice the winds high up in the atmosphere where our airplanes are flying are moving from west to east. And you can see they're moving pretty much straight west to east. Now, if we come up here to northern hemisphere, we will see a similar pattern, right? Where we see our winds flowing from west to east, but we see some bends, some wiggles in that flow. You'll also notice the difference, if I kind of maybe zoom out a little bit here and we just look, the difference between northern hemisphere and southern hemisphere right now has to do with the season. Okay, and we'll talk about why that is. Why is the southern hemisphere right now experiencing such strong upper level winds compared to the northern hemisphere? Okay, so what is happening is this unequal heating. Okay, so let's take a moment to think about, again, Earth in 3 dimensions. If we think about moving away from Earth's surface, warmer air will take up more volume than cooler air because the molecules will be closer together. And that goes back to that ideal gas law, PV equals nRT, pressure, volume, and temperature. So if I were to go to a certain height above the surface, let's say 5,000 not kilometers, 5,000 meters or 5 kilometers above Earth's surface. I literally got myself up there and now I'm going to walk on that height level of 5 kilometers. What I'm going to find is that here I'm walking on that height level, there's going to be more pressure above my head in the warmer part of the earth than there is if I'm over here in the colder part. There's actually, in this case, no air above my head. So I'd see no pressure. Okay, so at the same height in the atmosphere, there will be more pressure over warmer air because warmer air takes up more volume or more space. So when I am on an airplane flying way high in the atmosphere, over warmer areas, there'll be more pressure. So this would be higher pressure aloft and lower pressure aloft. Okay, so now we're thinking about what is the pressure high in the atmosphere? Now, where on Earth would we see the scenario of higher pressure aloft at some height? Where is it always quite warm? Yeah, the equator, which we call that region around the equator the tropics. Okay? And where is it going to be quite cool most of the time, or cooler most of the time? Yeah, our poles. Okay? So again, you could think of this as our poles. In this case, this would be our northern hemisphere or North Pole, and then our equator, tropics. Let me just put equator. Okay. So what's going to happen high up in the atmosphere is the flow of air above our heads wants to go from the higher pressure to the lower pressure. But we're in the northern hemisphere, it's going to get deflected to the right. Okay? So we call this the jet stream. High up where the planes are flying, the jet stream flows from west to east in our northern hemisphere. Okay? That's pretty cool because, let me keep these. We go back to this map, we can see that jet stream. So right now we're looking at 250 hectopascals at a height level, which is basically about what I'm saying, like maybe 7 kilometers, 5 to 7 kilometers above our head. We can see the winds are flowing mostly from west to east. And again, there's those wiggles, and we're talking about those. But that's pretty cool that we can describe the flow of our atmosphere based on temperature differences. All right, so that's northern hemisphere. Let's do it for the southern hemisphere. Again, our high pressure is going to be found by our tropics, and our low pressure will be at our pole. Okay, in this case, it's South Pole. And we can draw our winds at the high up in our jet stream. Want to go from high to low, but we're in the southern hemisphere, get deflected to the left. High to low, get deflected to the left. And oh, in the southern hemisphere, we also see west to east flow, westerly flow. Okay, so we'll keep those here and we'll go back and look, and we can see that's what we're seeing right here, right? The winds high up in the atmosphere in the southern hemisphere, the southern hemispheric jet stream is flowing incredibly fast from west to east. Now, there are some cool things that we can do with that jet stream, and we'll talk about those here in a second. But let's just recap, see if you're awake, paying attention. Which way are our upper tropospheric winds or jet stream? Which way are they flowing or blowing? All right. Yes. In both hemispheres, those upper atmospheric or upper tropospheric winds blow to the east, okay, from the west, okay? And in meteorology, we name our winds from the direction they come from, so we call those westerlies. They're blowing from the west to the east. Okay, so the answer here is A. And which month are the winds, our jet stream, our troposphere, upper tropospheric winds, the fastest in the northern hemisphere? All right. So, because we're focusing on the northern hemisphere here, the answer is January. A more simpler way to think about that is the jet stream, our upper atmospheric winds, are strongest during the winter season. Okay, why? It's because of the temperature difference, right? Our equator is going to stay basically the same temperature all year. But the difference is that our poles get super duper cold in the winter because it's 24 hours of darkness, no sunlight whatsoever. It's really cold. And so now, at the same height, there's going to be a greater pressure difference. And winds, the strength of those winds are due to the pressure difference. Okay, so our winter season, jet stream is stronger. And this is known as the polar front. Okay, it's actually the kind of boundary between the polar cell bringing cold air southward or towards the equator, and our ferrule cell bringing warm air from the equator towards the poles. And this location, around 60 degrees, both north and south, is where we get a lot of air mixing. Okay, a lot of cold air and a lot of warm air. Okay, and that's where we polar front, our jet stream, and this is where all the really cool weather is happening. And this is why the United States, for example, gets a lot of cool winter weather because we just happen to be along that jet stream path. Now, thinking about our jet stream, how can we use this in our daily lives? Which is going to be faster? Flying on a plane from LA to London, or London to LA, or Why are you asking me this? It's the same. All right. This is a really cool fact, a really cool phenomenon, right? Is when you're flying from the west to the east, it will always be a little shorter. Okay, so whenever we flew to France this summer, our flight from Denver, well, Denver to London actually was about 8 hours and 30 minutes. But when we flew London back to Denver, it was more like 9.5 hours. And that is because when you're flying with the jet stream pushing, the jet stream literally helps push the plane and you get there a little faster and you use less fuel. On the other way, coming back, you're facing those winds, you got a headwind, and it actually slows the plane down a bit. They have to use more fuel. So it's kind of cool. I think so. So now when you fly, think about that. Maybe you're flying even in the United States, just going from like California to, I don't know, New York. You'll notice how the time differences are in the different directions. Okay. And this is due to our jet stream. Okay. Now, our jet stream doesn't stay in a straight line, as shown in this top graph or this top figure. It actually starts to move. Okay. And that is the way in which our Earth system, our climate system, helps to bring cold air south towards the equator and warm air north. Okay. And flip that for the southern hemisphere, right? Cold air north and warm air south. It helps to redistribute that heat. That's our what we call Rossby waves in our jet stream. And we get a lot of action in our jet stream in the winter season. Okay. And you might have heard this called the polar vortex. Uh, it's not new. However, one thing that is happening with changing temperatures on our planet is that this jet stream will start to become more I guess, for lack of a better word, loosey-goosey in the sense that it doesn't stay as straight as west to east flow. It'll start to bend more, which means we'll see more winter storm outbreaks where we get these really cold air sinking south. A few years ago, this happened in Texas, where this Arctic air stunk all the way down towards Texas. And it was really bad because Texas's infrastructure cannot handle below freezing temperatures for several days. And, unfortunately, people died in this because they didn't, their electric grid failed and a lot of other not great things happened, right? So with climate change, our jet stream is going to become more kind of wiggly. And that is a scientific term, wiggly. Okay, so if we go back and look at our Rossby waves today, we can look at our atmospheric circulation, and you can see there's not as much Rossby wave action happening in Antarctica or in the southern hemisphere because it's just so gosh darn cold. But when we look up here in the northern hemisphere, we can see this big dip here off the coast of Japan, and we can see how we have a big dip here in the US too. Okay, so these ups and downs in our jet stream help bring warm air north and cold air south, help to mix the temperatures, mix that heat. All right. So that's our upper air, right? That wasn't explained by our 3-cell model. We had to think a little deeper to figure that out. Now let's go back to this specific heat. Which surface is going to heat up or cool down faster? Okay. What? There it is. Okay, so our land, yes, our land surface, it has a lower specific heat, so it's going to change its temperature faster when you apply some amount of heat to it, say sunlight. Now, this impacts what we call the land sea breeze. And you've definitely experienced this if you've gone to the beach in Southern California or any beach, is that during the day, both the water and the land are going to get the same amount of heat, right, from the sun, but they're going to heat up at different rates. And we know that when we heat air, it rises. And that is going to cause what we call a small scale circulation. The winds are going to pick up. And so what happens during the day over the land, that land heats up and creates rising air, warm air rises, and that creates a localized lower pressure right at the beachfront. And so air wants to come in from the ocean to fill in that lower pressure, to help make that pressure difference not so obvious. Okay, so we know everything flows from high to low. And so during the day, we get what's called a sea breeze, where we get wind coming off of the water towards the land. But at night, the opposite happens, right? So at night, the land cools down faster, creating a higher pressure over land, but our ocean water still stays warm. Its temperature doesn't change much. And so you get a lower pressure over the ocean. And so you have air rising over the ocean. And so at night, this circulation flips and you get what we call a land breeze, where the air is flowing or the wind is flowing from the land to the ocean. All right. So if you're at the beach during the day and you're facing the water, I'm looking out over my beautiful ocean, what direction are those winds going to be hitting? Are they going to be hitting you in the face or hitting your back? All right. Yes. So during the day, if you're facing the water, that wind will be hitting you in the face. And this is one of the reasons why, if you've been at the beach for a few hours, by the time you leave, your hair is like sticky with like salty water. Even if you hadn't been in the beach or in the water, it's because it's picking up that breeze as it's coming towards the shore, it's picking up moisture and salt from the ocean. And then, your hair gets all nice and beached. Okay. But the opposite is not happening at night because the air is coming from the land and it's not as salty and moist. Okay, so this is the land sea breeze. So this smaller scale circulation happens every day. We call that diurnal. And again, our 3-cell model doesn't know about this because it doesn't know where land and ocean are. But one of the reasons why people like to live near the coast or near lakes is because of this effect, that when you're closer to the water during the day, it stays cooler. When you're inland, it's warmer, right? So this is the difference between Irvine and Riverside during a hot summer day. Now, if we take that same circulation, but we make it happen over a season, we get what's known as a monsoon. Right now, we are getting a monsoon in southwestern the United States. And this is happening again because of the different heating and cooling rates of land. One of the most well-known monsoons is the Indian monsoon. And there are 2 seasons in a monsoon. You have very heavy precipitation or you're really hot and dry. Okay, it's like a land sea breeze. It's just happening on seasonal scales. Okay, and so what's happening again is during the summer, the land surface heats up more, causing air above the land to rise up. And therefore, ocean air that's rushing over the ocean, getting a lot of moisture, is coming inland and then rising up, forming clouds. And we're going to talk about that process later today. So you get really rainy season. Okay, so I actually have a video here. I just want to show you about the Indian monsoon. And when I talk about really heavy rain, a lot of times it's really bad flooding in these monsoon systems. So here we go. Here's a quick little video. This was just last month.
हालात काफ़ी ख़राब हैं। बड़ी भारी बारिश जो है पिछले 12-14 घंटे से जिला कुल्लू और जिला मंडी में हो रही है। तो आप देख ही रहे हैं कि ब्यास में कितना भारी पानी जो है ये आज आ चुका है। सामने पंचवक्र मंदिर जो कि लोगों का घूमने फिरने का इलाका है। ब्यास दरिया का जो रिवर बेड है यहाँ से बहुत नीचे है, लेकिन आप देख रहे हैं कि जहाँ हम खड़े हैं वहाँ तक पानी पहुँच गया है।
आज 9 तारीख को भी प्रदेश में रेड अलर्ट जारी किया हुआ है और जो डिस्ट्रिक्ट है जहाँ पे एक्सट्रीमली हैवी रेनफॉल का अलर्ट है, देखिए वो है कांगड़ा, चंबा, कुल्लू, मंडी, ऊना, बिलासपुर, हमीरपुर और जो बाकी डिस्ट्रिक्ट हैं आप जैसे सोलन।
All right, so very heavy rains, and this happens every season. Not every year do you get these catastrophic flooding and landslide issues, but as climate changes, as there's just more heat in the system, we do expect that these monsoon seasons will become even more extreme. Okay, so we have the Indian Asian monsoon over here. We also have the East Africa monsoon, the Australia monsoon, South America monsoon, and then North America. It impacts California, I almost said Australia, Arizona, New Mexico, even here in Colorado. It's been quite humid, more so than normal. Again, it's due to that temperature difference between the land and the ocean during the peak summer, right? The land has been heating up and it gets quite warm and creates that low pressure, and the air rushes in from over the ocean to fill that low pressure. Okay, so these are seasonal cycles. And lastly, we have something probably pretty impactful to you all there in SoCal is Santa Ana's. Okay, these are actually not driven by temperature differences per se, right? They're not caused by unequal heating of the ocean and the land. Rather, they are caused by differences in pressure systems on land. Okay, so for example, if we have a higher pressure, like a weather pattern, where there's higher pressure in the Great Basin and a lower pressure near the coast, the surface air wants to flow from high to low pressure. But what happens, there's two things that happen with Santa Ana's, is the air is coming down in elevation. It's coming from higher mountains to lower sea level. And that change actually heats up air. And we're going to talk a lot about that today, but we call that adiabatic compression. So the air heats up as it goes from higher up to lower in the atmosphere. And because there's a lot of canyons and mountain ranges in between, those winds get funneled and they speed up. Okay, so there's a few things going for it, right? We have very high speeds and they're very warm and dry. And this is usually, not always, but usually when we have fire issues, wildfire issues in Southern California, is because of these Santa Ana winds. Okay, so maybe you haven't experienced them just yet. So I have a video showcasing what these Santa Ana winds look like and are.
Santa Ana winds are one of Southern California's most recognized weather features, especially from the fall to the spring.
It's one of the most impactful weather patterns we can have in Southern California. I mean, everybody hears about the wildfires in Southern California, and the driving force behind that are these Santa Ana winds.
These are northeasterly offshore winds that descend in elevation and can sometimes reach hurricane force strength.
So when you get the very hot, the very dry conditions combined with very strong winds. We can have some Santa Anas that have winds gusting over 100 miles per hour.
These winds originate from high pressure over the Great Basin with low pressure off the coast. Winds flow from high pressure to low pressure, and the stronger the gradient or pressure difference between the two, the stronger the winds can be. As the winds get closer to sea level, they speed up, dry out, and heat the air.
It can actually warm on a rate of almost 30 degrees Fahrenheit per mile.
The combination of hot, dry, and windy conditions contributes to a number of changes to the weather, including record-setting temperatures and, most notably, dangerous fire weather conditions.
Fire has crested this hill here.
I would say that our strongest Santa Anas are probably in the early morning hours, say just before sunrise and just after sunrise, when you have a better chance of having very hot temperatures. That can naturally bring that relative humidity even lower in the afternoon.
Santa Anas last around the clock, sometimes days in a row, with little to no relief. Fortunately, forecasters are able to spot this pattern up to 6 to 7 days in advance.
We may not have the...
All right, so Santa Anas. Again, not driven by land-ocean difference, but driven by pressure between higher weather pattern and higher pressure weather pattern and lower pressure on Earth's surface. Okay, so again, they're warm and dry to this adiabatic. We're going to talk about this. I know it's a little out of order, but just with the flow of winds here, basically air is going to be compressed as it sinks down to the surface, and that compression heats up the molecules. And that compression occurs at roughly a rate of 10 degrees Celsius per kilometer. So let's think about this. If I have my air and it's starting out at the mountains, which have an elevation of 3 kilometers, and they're being forced down to the SoCal coast, which is at sea level or 0 kilometers, and the air is actually freezing temperature, starting at the top, what's the temperature of that air going to be when it gets down to SoCal? Okay. So it's 10 degrees per kilometer. We're starting at 3 kilometers. So it would be 10 degrees C times per kilometer times 3 kilometers. And that's going to give us 30 degrees C increase in temperature. And we started at 0. So I made that math easy. So plus 30 gives you 30. Okay, so you're going from freezing temperature to very, very hot just by bringing that air down in elevation. Okay, and that leads us into the hydrologic cycle. Okay, so remember that the latent heat of vaporization requires lots of heat energy. And where does that energy come from? It's coming from water. And we're moving water around our planet, okay? And so the big way, our big reservoir of water is our oceans. We evaporate water from the ocean, we take it onto land, and then it flows through the land surface and ultimately ends up back in the ocean, okay? Also remember that our temperature in our atmosphere decreases with height, okay? So if we look at our troposphere, this bottom layer where we are, as you move higher up in altitude or elevation, temperature decreases. In our stratosphere, temperature increases because of the ozone layer. But for us right now, the troposphere, temperature decreases with height. So Why do we get precipitation? Why do we get rainfall and snowfall? What's happening is that when air is rising, right? We talk about air rising up from the surface. It's cooling too, because the environment around it is also cooling, right? We know that temperature decreases with height. So air rises, it cools. And when air cools, it can reach saturation. And when that saturation process happens, we can condense those water vapor molecules into cloud droplets, and that might lead to precipitation. And that's a latent heat exchange process. So I'm going to talk about those terms now. What do I mean when I say saturation? So what I'd like you to do is imagine I have a chamber here, a closed chamber, have some water in it. Initially, the air above the water is absolutely dry. There's no water vapor, no moisture in that air, 0% humidity. Over time, that system is not in balance. The dry air is thirsty. It wants to take up, it wants to evaporate some of that moisture in order to have equilibrium. And so what's going to start to happen is you'll have evaporation. There will be some condensation, but initially there will be more water vapor molecules evaporating than condensing. What's also going to happen is if we had a pressure gauge, we would see the pressure rising because water molecules have a mass and they would exert a force per area or pressure. Over more time, we will reach what we call equilibrium, where the evaporation rate equals the condensation rate. And we will get some measure of pressure, and that pressure is what we call the saturation vapor pressure, or the maximum amount of vapor that can be in that system at a given temperature. Okay, so some terminologies I'll be using are vapor pressure. Also, we can sometimes call this mixing ratio. They're very similar and interchangeable. It's the pressure of water vapor in the atmosphere, if we're calling it vapor pressure. We're physically measuring the force that that water vapor is exerting. Mixing ratio is how much moisture there is in terms of grams per kilogram of air. As I mentioned, equilibrium is the rate at when evaporation equals the rate of condensation. And saturation is the point where the amount of water in the gas phase, that evaporated water, that water vapor, is maximized. And saturation is a function of temperature only. So if you know the temperature of the air, you know the amount of water that can be maximized, or the amount of water vapor that can be maximized. Okay, that's temp. And then we have, again, as I mentioned, saturation vapor pressure, or the saturation mixing ratio. And that we know is a relationship with temperature. Okay, it looks like this. On the x-axis here, I have temperature in degrees Celsius. On the left axis, vertical axis, I have water vapor, and this is in mixing ratio. So it's grams of water vapor per kilogram of air. So basically, how much water vapor do I have in my unit of air? The blue line here is the saturation mixing ratio. And this tells me that at any temperature on the x-axis, that is when I've reached that equilibrium, that evaporation and condensation are equal. That's the most water vapor I can have in that air. And that is a thermodynamical principle, okay? What you'll notice is that warmer air can have more moisture in it before saturation occurs. For example, a 40-degree C sample of air can have about 45 grams per kilogram of water vapor in it at saturation, but a 10-degree Celsius sample of air can only have about 7 grams per kilogram. And so warmer air can thermodynamically hold more moisture than colder air. Okay, so what I'd like us to do right now is let's pause on this. Let's take a moment to decompress. Let's go ahead and take a 15-minute break. Yeah, and let's meet back at 2:50, and we will continue on with this discussion. All right, so we will come back and think about this idea of saturation and the idea that at certain temperatures, the air in our climate system can reach saturation. Okay, so here we're going to look at some examples of how to read information off of this figure and also how to interpret information from this figure. So let's look right now. Here is a little parcel or unit of air, and my unit of air is shown here with this black dot. So looking at this information, what is the vapor mixing ratio of my parcel of air? How much vapor is in that sample of air? All right. So when we look at this information, this is a sample of air, right? So if I could just go outside right now and I measure the air and how much vapor is in it, the way we read this graph is we go to the left here. And the answer here is 5 grams per kilogram. That's how much vapor, water vapor, is in that sample at that moment. If you answered 20 grams per kilogram, what you're looking at is the saturation mixing ratio. How much water vapor would be necessary for that sample to be at saturation? Okay, but in this case, my air is not at saturation. It's well below it. It only has 5 grams per kilogram. Okay, and then we can think about what is the temperature of my parcel of air. And I don't have this as a poll. I forgot to add that. So just type into the chat, what is the temperature of the sample of air? Great. 25 degrees C, right? So we're just going to read down here. And so we see that we're at 25 degrees. Perfect. Okay. So that's the temperature and how much vapor is in that sample. Now we can do a few things with that air, right? We could go to the right. We could increase the temperature. We could go to the left. We could decrease the temperature. We could add more vapor, or we could decrease the vapor, right? There's like these kind of 4 directions we can go. Now, if I look at this graph in a little more detail, what it's telling me is that anything over here to the left of this blue saturation line is telling me I am saturated, or actually super saturated, meaning I have more vapor in that sample of air than the sample really wants to have, because we're past that blue line. Everything to the right here means we're under saturated. Okay, the air is thirsty here. It can still have more moisture in it before it reaches saturation. And remember, the blue line itself is saturation. So there's really only a fine line, pun intended, I guess here, of where saturation occurs. All right, so if I increase the temperature, I'm going to become unsaturated, or even more unsaturated. If I decrease the temperature enough, I will cross that blue saturation mixing ratio line, and I'll become supersaturated, and condensation will take place. And if I add more water vapor, then I can also cross that mixing ratio line, that saturation mixing ratio line, and become supersaturated again. Okay, so what temperature, oops, would the air parcel, here's my air parcel here, reach saturation if no water vapor is added? Alrighty, so if we're not adding water vapor, if we're not going up to reach the blue line, the only way we can get to the blue line is decreasing the temperature. Okay, so what's that temperature? We're gonna follow along. We're not adding or removing water vapor. So where we cross that line is 5 degrees C. Okay, that temperature that we just discovered, 5 degrees C, is what is known as the dew point temperature. It's the temperature at which saturation occurs, and it's based upon how much moisture is already in the air. And it's always less than or equal to the actual air temperature. When the dew point temperature is a larger or higher value, it means there's more moisture in the air. And it's a useful measure of water vapor abundance. You know something about the dew point temperature, it gives you a sense of how close that air is to being saturated. Okay, so dew point temperature is a temperature. So we can measure atmospheric moisture by looking at vapor pressure, but that's not something, I just know. Like, you don't go outside and be like, oh, there's 5 grams per kilogram of moisture. That's not something most people are going to use. Dew point temperature is pretty common, but one that is used more frequently is relative humidity. Okay, but yes, dew point, the reason it's called dew point is the temperature where that saturation occurs, and it's usually when we see dew form on grass or spider webs, right? And this usually happens overnight. When temperatures decrease overnight because the earth has been sending away heat all night but not receiving heat from the sun, the coolest part of the day is always right before the sun rises again. And that's usually when we can sometimes reach that dew point temperature. Okay. So here I have two samples of air, A and B. They have the same temperature. Which one has the higher dew point temperature? All right, so with this, the way to do dew point is you just take that sample of air and you move it to the left. Whoops. And wherever it crosses that blue saturation line, that's the temperature. So in case of parcel B, the dew point is something like maybe 28 degrees C or so. And then parcel A is, again, that same sample. It's 5 degrees C. Okay, so we can see what I just said in this graph, that the more moisture that's in the air, there will be a higher dew point. Okay, and that has to do with the shape of this curve. Okay, and parcel B does have much more moisture. It has 25 grams per kilogram of moisture versus A here, which is 5. Okay. Some other ways we can look at this graph. At what vapor mixing ratio would the parcel of air reach saturation if we hold temperature constant? All right, so in this case, we're holding temperature constant, so we're not going to go to the left here. We're not looking for dew point. What we're just going to do is move up and find where that intersection occurs, which is about 35. Okay, so in this case, how could we get this sample to saturation? Well, we'd have to add moisture. Maybe we have more moist air mixing with this drier air. Okay, so relative humidity, I guess I jumped ahead a little bit, but relative humidity is another way that we quantify moisture in the atmosphere. And it is a ratio. It is the amount of water in the air expressed as a percentage of the maximum amount possible. Okay, so it's the actual vapor, how much is actually in that sample, over the saturation vapor mixing ratio or pressure, depending upon the different figure you're looking at. So it's looking at what we just did. How much is in the sample versus how much we need to be saturated. Times 100% to give you a percentage. All right, so the actual vapor mixing ratio in this sample was 5. Okay, we're just going to read it from the left here. Going to the left axis, it's 5 all the way over. Okay, so 5 grams per kilogram. And the saturation mixing ratio is where we have to go all the way up till we cross the blue line, and that's 35. Okay, and remember, saturation is a function of temperature. So all you need to know is the temperature of a sample of air, and you'll know how much this denominator should be. That's always true. And so we can do this math here. Our relative humidity is going to be 5 grams per kilogram over 35 grams per kilogram, and the whole thing times 100%. And so when we do the math, I always forget to have this done. 5 divided by 35 is 0.14. times that 100% gives you 14%. Now, another way that I sometimes like to think about relative humidity is it's how far along you are the journey to saturation, right? So imagine here's my road to saturation. Here's my road, okay? The end of my road is saturation. Right now, I'm in my car and I'm only 14% of the way to my destination of saturation. Okay, so the further away you are from the blue line, that blue saturation curve, the lower your relative humidity will be. The closer you are, the higher your relative humidity will be. If you're on the blue line, you have 100% relative humidity. It is possible to have greater than 100% relative humidity. It happens. It doesn't go really above about 104% in nature, but it can happen. Now, why do we care? Well, humidity, relative humidity, is a really great measure of moisture that we understand. And I tell you it's low humidity, you probably understand that it's going to be dry, right? Those Santa Ana winds have very low humidity, like 10% or lower. And humans have adapted to this idea of humidity, or the ratio of how much air, excuse me, how much vapor is in the air versus saturation. When we sweat, that process I mentioned of evaporation happens, right? We have our sweat, the moisture comes to the surface, and when evaporation occurs, that pulls that moisture away and it cools our skin because the heat needed for evaporation is coming from our skin, that latent heat flux. Now, the problem is in really high relative humidity environments, the evaporation rate is low because the air already has a lot of moisture. It doesn't want your skin's moisture, it doesn't want your body's sweat. Okay, so you don't cool down as quickly. At the same temperature, where you have lower humidity or less moisture in the air, it will feel nicer. You can exercise outside, you'll cool off quicker because the air is thirsty. Dry air is thirsty air. It's trying to get moisture from any way possible, and your skin's a great one. Your sweat is a great one. So that's why people like living in Irvine, for example, because it has lower humidity than other places. So ways we can saturate air with water vapor is we can add water vapor to the air. Okay, just put some water vapor in. We can decrease the temperature of the air. Okay, that's our dew point. You can have frost point, which is just a freezing, below freezing. Fog and clouds are that same concept. We've decreased the temperature of the air enough to have saturation, and we've formed clouds. You can also mix cold air with warm, moist air, but decreasing the temperature of the air. How clouds form is through this temperature change. As I mentioned, as we move higher in the atmosphere, in the troposphere, temperature decreases. And that lapse rate, the temperature change per height, is about 10 degrees C per kilometer. Okay, so this says 9.8, but for this class, just 10. 10 degrees C per kilometer. That is if you have not yet reached saturation. So if the air is not fully saturated yet, it's considered dry. It still wants to have moisture. And so that's the dry lapse rate. Now, when we reach saturation, which is when the temperature reaches the dew point temperature, so where temperature gets cool enough to reach the dew point temperature, that is saturation. Okay, and that is also known as the level of condensation, and that's where we start to form a cloud. At that point, we know that during condensation, heat must be released. And so our lapse rate, how temperature changes as that air is rising, is now lower. It used to be 10 degrees C per kilometer, but now we're releasing some heat from that latent heat exchange. And so the lapse rate is more like 5 to 6 degrees C per kilometer. Again, because we're taking some of that heat that was in the molecules of vapor, and then it's being released as that vapor gets condensed down back to liquid. So clouds are not vapor, clouds are liquid droplets of water. Okay? So how do we change the air temperature? You can add or remove energy through radiation, conduction, sensible heat. You can mix warm and cooled air. You can change the phase of water. But these are all called diabatic processes, where we're actually taking energy and adding it or removing it. Another way that we can change temperature without adding or removing energy is by changing the pressure. And we can change the pressure of that sample of air by moving it up in the atmosphere or moving it down. Because we know that as you move higher in the atmosphere, the pressure decreases. There's less molecules of air above you. And as you come down in the atmosphere, closer to the surface, atmospheric pressure increases. Okay? So compressing air heats it up, expanding air cools down. It looks like this. When air rises up, it expands. So rising air expands and cools at a lapse rate, depending upon the humidity of the sample. Is our sample dry or below 100% humidity? Then it will rise at 10 degrees C per kilometer. Once it is fully saturated, it will cool at the moist or wet lapse rate of about 5 degrees C per kilometer. Now, again, you're like, wait, how do I get to dew point temperature? Well, you're going to get to dew point temperature if the air's cooling off, right? So if I start at the surface and my air is 32 degrees C, and I tell you, hey, right now that sample has a dew point temperature of 2 degrees C. Where will the air reach saturation? Well, it's going to rise up 1 kilometer and cool down by 10 degrees. It'll reach another kilometer above the surface and be 12 degrees C, and then another kilometer. Oh, now my sample has reached the dew point temperature of 2 degrees C, and now I'm going to start condensing out that water vapor to form a cloud. Now, when you start to bring air back down to the surface, say in our Santa Ana wind scenario, that sinking air gets compressed and it heats up. So air that has not reached saturation will always follow the dry adiabatic lapse rate of about 10 degrees C per kilometer. Air that has reached saturation, where the temperature is now equal or less than the dew point temperature, we consider that saturated air, and it will cool at the moist or wet adiabatic lapse rate of about 5 degrees C per kilometer. Okay, so here's an example. This is how we form a cloud. The air rises up and the temperature starts to decline. And in my case here, my sample of air is going to have a dew point temperature of 10 degrees. Okay, so dry adiabatic lapse rate of 10 degrees, and I'm starting at 20 degrees, which means that after 1 kilometer, I've already reached dew point, right? Because 20 degrees C drops down to 10 degrees C, and that equals the dew point. Okay, so you see that here. We start at 20, at 1 kilometer, this is a meter, so 1 kilometer, dew point temperature and the air temperature of that sample are the same. We've reached saturation, and then condensation starts. That condensation process releases heat back to the environment. And so the heat release decreases the rate of cooling. And now that air, if it continues to rise, which usually it does, will now cool at a slower rate. So here's an example. Here's my cloud, beautiful storm cloud here. Where in this example, C, kind of in between the surface and the cloud bottom, B or A, is the air reaching its dew point? Right. Okay, so B is correct. So what's happening here, right, is our air is rising up. Why is it rising? We'll get to in a second, but it's rising up, okay? And as it's rising up, that's not a good color. Let me do red. As it's rising up, it's dry, not saturated. At this level, which you can see in the cloud is actually a perfect flat surface, the T equals the dew point. Temperature equals dew point temperature. And now we are saturated. So where would the air be cooling at the dry lapse rate? A, B, or C? All right. So once the air reaches the dew point at B, it's going to continue rising up at saturated air. If you see a cloud, you see how it's white. What you're seeing are cloud droplets, liquid droplets. So this is all saturation. So this would all be wet or saturated lapse rate. The only place where it's rising at the dry lapse rate is down here at C. So between C and B, the air is not yet saturated, so it would be rising at the dry lapse rate. So the answer here is C. Now, that stole my punchline. Where is the air cooling at the wet lapse rate? After B and all the way to A, and past A, technically. All of this, anywhere you see a cloud, anywhere you see the droplets, is the wet lapse rate. Until all of the vapor is condensed out, it will cool at the wet lapse rate. And then that takes us further than this class needs to go in terms of thermodynamics. But that is how this cooling process works in our atmosphere. The reason we get clouds is because the air cools and reaches its saturation temperature, dew point, condenses out the moisture to form cloud droplets. Now, how do we get air to rise up or get lifted? Well, we know warm air rises. Warm air can rise. We can get warm air through a series of things. The first is what's known as convergence lifting. So let's say you have a lower pressure on Earth's surface, like a weather pattern, where we have lower pressure. The air is going to rush in from all directions, and the air will it will converge. And it can't go down into Earth's surface, so it rises up. And that convergence creates air rising up. We can have localized convection, where different surfaces of Earth heat and cool at different rates. And we can get warm air that rises up. And you can get clouds. We also have orographic or mountain lifting. So big mountain ranges like the Rocky Mountains, they cause air. The air has to go up and over. And as the air is forced up on the one side, it's being cooled. It has to cool down. And sometimes, if there's enough moisture in the air, saturation occurs, you get clouds. And this is the windward and leeward effect, where we get a lot of precipitation on the windward side of mountains. There's much more greenery, vegetation on that side. And then on the leeward side, as the air is being forced back down the mountain, all that moisture has been removed. And now the air is heating, and it gets really dry, hot air on that leeward side, and we get a lot of deserts on that leeward side of mountains. And we can also have air rising at what we call fronts. So where we have air of different temperature, we get these frontal boundaries. So for example, here's cold air mixing with warm air. Warm air is less dense, will rise up. And so we get storms along these fronts. So that's how we can get air to rise. And that's why we get clouds. Oftentimes, especially during like warm days, it's just this localized convection that's happening. So clouds. Now, you do not need to know all the different clouds. I don't even know all the different clouds. What we need to know are the differences in high and low clouds. All we care about are that some clouds are much higher in the atmosphere. We call those cirrus, these wispy ones way up high. Those are made mainly of ice and ice crystals. And we have lower clouds, like our stratus clouds. That's what causes June gloom, fog. Those are stratus, low. And why do we care about high and low clouds? Well, high clouds are going to result in a net warming effect, and low clouds result in a net cooling effect. Okay? And so when we think about climate change and the fact that temperatures are getting warmer, there'll be more evaporation, which that could lead to more clouds. Where the clouds are they cirrus? Are they high? Are they stratus and low? Will determine the impact on climate. Now, that's something we can't really model and project out into the future. So that's why we're uncertain about clouds in terms of the impact on climate. Okay. Now, I want to emphasize that clouds do not always equal precipitation. If we look at these images or these little icons here, these are basically demonstrating the size differences between a cloud droplet. This is a typical cloud droplet. Here is a large cloud droplet. And then at the bottom here, this curvature is the typical rain droplet size. So some clouds will cause precipitation and some clouds don't. And that's because the droplets must get big enough to overcome the upward rising force. And they have to get big enough to fall. Gravity has to be able to pull them back down to surface. That's the terminal velocity. And so not all clouds will lead to rain or precipitation because those droplets are just not big enough. So why does it matter? Okay, just again, going back to this idea that the equator is heated all the time. And so we have a lot of evaporation occurring. Some of the moisture, a lot of the moisture that's evaporated in the tropics is precipitated out as rain or snow up in the mid latitudes, up in the polar regions. And so this is moving heat from one aspect, from one area of the earth to another. And this is how we can redistribute a lot of the energy around the Earth's surface. Okay. Questions? Okay, so now we're going to talk about residence time. But first, we need to talk about some vocabulary. When we talk about a reservoir, we are talking about where something is stored for a long period of time. Now, in this case, because we're talking about water, you may know of reservoirs, right? We use dams to store water on Earth. We call those reservoirs. But other things can have reservoirs. For example, carbon. We talk about carbon dioxide. The atmosphere is a reservoir for carbon dioxide. So is the ocean. So is the Earth's surface. So a reservoir is just where something is stored. A flux is the movement of something between two locations. Right? We talked about flux in terms of solar energy, but we can have a flux of water from the ocean to the atmosphere. And whether or not the material is coming into the reservoir or leaving, we can call it a source or a sink, right? A source is an addition to that reservoir, and a sink is a removal out of that reservoir. Okay? So when we look at our water cycle, what are some of the major reservoirs of water on our planet? You can just type your answer in to chat. Where is a lot of water stored on Earth? Mm-hmm. Yep. So the oceans are a big reservoir, glaciers, rivers, lakes, the atmosphere. Okay. So when we think of these cycles, and we're going to start really diving into these cycles, we have to think about where a lot of that thing is. So in this case, we're talking about water and how it's moving around. Okay. So reservoir, the amount of material of interest, the source is material added to that reservoir, a sink is material removed from the reservoir. When a system is in steady state or a reservoir is in steady state, it means that the sources into the reservoir equal the sinks out. What's coming in is equal to what's leaving. And so the system, our reservoir, is not changing size. Okay, steady, right? Not changing. If a reservoir is in steady state, it allows us to calculate what's known as residence time, which is how long one molecule of your material will stay in that reservoir on average. Okay, so in this case, if we're talking about water, the residence time of water in the atmosphere depends on the amount of water in our atmosphere and how much is coming in or leaving. We'll do an example. When we think about steady state, though, we can visualize it pretty easily. So here are some examples of water reservoirs. Oops, wrong one, sorry. Would we consider these water reservoirs to be in steady state? All right. So the answer here is no, because steady state is what's coming in is what is leaving. Now, there's a little context here that I didn't tell you, but this is Lake Oroville. And this was in 2017, I believe, where there was a lot of rainfall and the dam was about to break. So they were releasing a bunch of water. Okay. So there was much more water leaving than coming in. So not steady state. And in this case, this I think is Lake Powell, where you can see there is a lot more water leaving than coming in. The level has dropped. Okay. It's hard to show steady state in a picture because you don't know what's happening, but these are not in steady state. So here's an example of residence time and calculations. Okay, so imagine we're going to talk about my fictitious bank account. If my income, so here's my bank account, bank. If I have income of $2,000 a month, and I have sinks, 1, 2, 3, 4, 5 sinks, and those are my sinks here, like rent, food, car, savings, and fun money. My question for you is my bank account in steady state? So I actually have this question here. I want you to think about it. Look at the numbers and tell me, is my bank account in steady state? All right. So the answer here is yes, because the money coming in, the source of money into my account, my bank account, is equal to the amount going out. It doesn't have anything to do with the numbers of fluxes, right? Because on the income side or the source side, I only have one flux, and I have 1, 2, 3, 4, 5 fluxes in terms of sinks or ways I'm taking money out of my account. Those 1 and 5, that doesn't matter. You could have as many fluxes out as you want. What matters is that the values are the same. So my income is 2,000. If I sum up my bills, 800, 300, that's 1,100, 1,500, 1,800, and then I get 2,000. Okay, so source and sink equal, I'm in steady state. This means my bank account is not getting bigger or smaller through time. Not ideal, right? You want to have some savings, but also I'm not going into debt, so that's good too. All right, here's another example. UCI has about 20,000 students. If 5,000 first-year students arrive each year and 5,000 students graduate each year, what is the residence time of a student at UCI? Okay, so the equation is there for residence time, and I always laugh because there's some of you that choose forever. I promise you it's not forever. It sometimes feels like it, but I was at UCI for almost 7 years, so I saw like 2 groups of students move through, and that feels like forever. So residence time is reservoir. Our reservoir in this case is students. And there's 20,000 of y'all. So 20,000 divided by the total source in or the sink out. You don't have to add them together. So it is 5,000. So 5,000, oops, 5,000, forget that zero. So 20, the zeros cancel. 20 divided by 5 is 4 years, right? So the average time a student stays at UCI is 4 years. Now, another example of residence time. I have a 50-liter bathtub and it's full. And it can drain 5 liters per minute. If I take out the plug, what is the residence time of water in the bathtub? And how fast would water have to flow in from the faucet or the tap to create steady state? Okay, so way we do this is really, though, we should think about steady state first, because you can't do residence time calculation if the system is not in steady state. So if I'm draining at 5 liters per minute, it means I also have to be adding water at 5 liters per minute in order to be in steady state. So that pretty much gets rid of everything except for C. Okay, and then we can take 50 liters divided by 5 liters per minute, and then we get 10 minutes. Okay, so if you were to do this, which I do not advise, very wasteful, you turn on the faucet. If the flow out is at the same rate, in this case, it would take about 10 minutes for a molecule to move through that bathtub. Now, here are some more Earth-related examples. Imagine the Salton Sea, which is down there in Southern California. It's a reservoir of water, it's a lake, and it has about 9 cubic kilometers of water. Now, the fluxes for our Salton Sea is that there's some river inflow, which is a source, of about 1.5 cubic kilometers per year. The way water is removed from that lake is through evaporation, and that's 1.5 cubic kilometers per year. So if our source in equals our source or our sink out, then it is in steady state, right? So river inflow is 1.5, check, and evaporation is 1.5, which means the lake level will not change. What's coming in is equal to what's going out. Unfortunately, in real life, this number, evaporation, is now higher than what's coming in, and so the level is dropping, which is leading to a lot of environmental problems. What's the residence time for water in my Salton Sea? Okay, so the answer would be about 6 years. So the way we do that, right, is it's going to be the reservoir, which the reservoir size is the lake, 9 cubic kilometers divided by either the flow in, the source in, or the sink out, the total value of that. So in this case, it's 1.5 cubic kilometers per year. 9 divided by 1.5 is 6. years. Right? Now we will see that our systems can be a little bit more complicated, right? We could have multiple sinks out and only one source in, and we have to, think about, is our system in steady state? And so when we talk about the carbon cycle, which we're going to spend like a whole week on the carbon cycle because it's so important to our Earth system, it's complicated because carbon is moving around at different rates and the reservoirs are of different sizes. So we have to think about our residence times. Okay, so that is all I have for you today. I am happy to stick around and answer any questions you have about the homework. But otherwise, I'll see you on Thursday. Don't forget, homework is due tonight. The check-in, daily check-in is available for you today as well. And I'll see you on Thursday. Bye.
So just to clarify, Professor, we only need to turn in the completed Word document.
Yes, that's correct.
All right. And yes, and this is going to be graded on, so just confirming last bits, it's going to be graded on correctness, and you're not going to drop the lowest grade.
For homeworks? For homeworks, not, I'll see how you all do. So we'll see what happens
Okay, thank you.
in terms of
I'm
homework.
not fully confident on everything, but I put my effort into it. I
Yeah,
think that goes for everybody else.
Yeah, absolutely. And some of these answers for your homework, there's no right answer, right? In terms of like, what is your rebuttal to a climate change denier, right? Obviously, I want to see if you are getting along the right tracks. So there's like no like, this is the answer for that one. But we're going to be grading with the idea that some of these discussions, you have to use the evidence to come up with a rebuttal. So there, my answer key in terms of how it's graded is pretty loose. So.
All right, thank you very much. Have a nice day.
You're welcome. You too.